Hello and welcome. I hope you are having a great day. In this video, we'll understand some optimizations in the k nearest neighbor algorithms. Earlier, we have seen the brute force algorithm of the k nearest neighbor. Okay, and now we'll see the optimizations that will make it ready for use for large data sets, which is very common in the industry. Okay, let's begin. So this is your k nearest neighbors. A quick revision. So the teacher is saying, show me your friends, your closest neighbors, and I'll tell you who you are. So it goes with the saying that you are the average of the people whom you hang out with. Okay, so that's your k nearest neighbor. Okay, so we have to determine whether this circle, the new circle that is coming, that whether it's a red type or blue type, and since it is closer to the red type, so we say that okay, you're also red type. Okay, that's the recap of what we have seen in the last class. Let's continue. So optimizations. So the naive KNN, okay, or the brute force KNN, okay, needs some improvements to fix some of its drawbacks. So what are the drawbacks? The data need to be standardized, and then distance weighted, the impact of distance, if the neighbors are too close or if the neighbors are too far, okay, what it should be adjusted for that. And then Mahalanobis distance, we'll see what is the impact of this. Okay, when do we use, and we'll see some more advanced optimizations that are used currently in the industry, but I'll just mention them. I won't go into the depth. I'll give you the concepts for this. Okay, and later in future I'll create separate videos for each one of them. But for understanding KNN, that is not required as of now, but I'll mention and give you a brief overview when I go to the advanced optimizations in this video itself. Okay, let's continue. So what is standardization? We have seen this in data pre-processing also. Standardization simply means mean centered and variance scaled. So is centering, it is, you are centering the mean to 0 and scaling the variance so that the variance becomes 1. You divide by the variance, so the variance is scaled down to 1, and you subtract the mean. So your mean, wherever your mean is, you subtract the mean from each data point so that your mean comes back to 0. So this is standardization. We do it because, so what's the use case? Say one feature is your annual income, which is if the range 0 to 1 million, and the another feature is years of experience, if I'm predicting what will be the salary in IT industry. Okay, so there is annual income. Okay, annual income, and then not the salary. This is not the right thing. Okay, let's forget this. But say for example, this is your salary is given already. So you have a salary and years of experience, and you are predicting something else. These are the two input features. So this, if you see the range, so this is like 0 to 10 to the power 6 one's annual income, and years of experience is 0 to 40 years only. So the range of values these two input features are taking is quite different. They are of different scale itself. So when we do the comparison, when we are comparing the distances, the Euclidean distance will be almost entirely dominated by the income because it is of larger scale. So when we calculate the distance with respect to all the features in the higher dimensional space, so this features distance will be very high and the smaller features will be very small, so they will have that less impact. Okay, so that's the drawback of this. So that's why we need to standardize them so that each feature, annual income, okay, and what is the years of experience, all of them have the same impact on the final outcome of the whatever we are trying to predict. Okay, let's see an example and you will understand it. Say for example, we are comparing an elephant and a rabbit. Okay, so here's a rabbit also. Okay, so the elephant is 5000 kg and the rabbit is 2 kg, and say the elephant's speed is 25 km per hour and rabbit's speed is 45 km per hour. So if you compare the distance, Euclidean distance, so this is 499, it means 5000 minus 2 whole square plus 25 minus 45 whole square root. So if you see, the distance is dominated by the weight because it is too high. 5000 minus 2, this distance is very this is the prominent feature, and here this is very small. So there we have to make it that both the features become comparable, and for that we will, and if you compare only this, then you can say that okay, elephant is very good, a rabbit is nothing in front of a elephant then. But we have to make a valid comparison of elephant and rabbit using both the features, because we are also calculating speed and rabbit is faster than the elephant. So yeah, we'll standardize the data with respect to, we'll take the average weight of all the animals in the forest and the average speed of all the animals in the forest, and then we'll make the comparison. After that, we'll see that the rabbit is not so light. It is just minus 0.5 sigma or standard deviations away from the mean, and but the elephant is heavy. He's like plus 3 sigma away from the mean. Sorry, but if you see the speed scale, so the elephant is like minus 1 sigma slower from the mean, and the rabbit is like plus 2 sigma. Okay, plus 2 sigma faster. So here he's minus 1, so the distance here is like 3 sigma here, and here the distance is like 3.5 sigma. So now you see they have become on the comparison on is on kind of on the same scale. So now weights difference sorry, will be 3 minus minus 0.5. So it's in terms of standard deviation, and this will be like 2 minus minus 1. Okay, so now they have become in the comparable range. Now the weight will not overwhelm. So now if we calculate the distance after standardizing the data, so this will be like kind of square root of 3 minus minus 0.5, that will be like 3.5 square plus 3 square, like that. So if you see, this will not be, this is 2 minus minus 1 will be 3, and 3 minus minus 0.5 will be 3.5. So now you see this is not dominated by weight itself. Okay, so this is 3.5 standard deviations difference, and here this is just 3 sigma standard deviation, the speed. So this has now become comparable after standardization, and both the features weight and speed are now comparable, and that's what is the importance of scaling or standardization. I hope that is clear with this example. Okay, let's continue. So the other optimization that we do is distance-weighted KNN. Okay, so the vanilla or naive KNN treats first nearest neighbor and the kth nearest neighbor as equal. All the nearest neighbors are same for me, because we just need the count, like k equal to 5 or 10, whatever nearest neighbor we want to find. So all the neighbors are same for me. Okay, that's what a simple or naive KNN does. But is it the case? No. So the neighbor that is 0.1 units away should have more influence than a neighbor which is 10 units away, right? The neighbor who is closer to me should have more influence on me than the neighbor who is farther away, right? That's the real case. A friend who is close to you has more impact to you than the friend who is farther away from you. The closer friend has opinions have more weightage on you than friend who is like a distant friend, right? That's what we do. Whatever is there in the real world, we just replicate that in software world or machine learning world also. Okay, and generally we assign a weight to each neighbor, and most common strategy is inverse of square distance. So we take the distance square, and the weight for each neighbor is given in proportion to the inverse of the square. This epsilon is added as a factor, so that if distance is 0, so this 1 by 0, this doesn't become undefined infinity for computation. So we keep it as a small value. That's the computational hack. So what does it do? It improves. It improves reduces the impact of noise or outlier or distant neighbors. They are very far neighbors, even though like it is very sparsely distributed, and we have one data point. So if there is an outlier which is very far, so and we are counting k, so 3-4 neighbors are very close and the fifth neighbor is very far, but still that neighbor will also have the same impact as the 4 close neighbors. So this, if we give weight to the neighbors on the base of the distance from me, so that will reduce the impact of the noise or outlier which is farther away. Okay, also the imbalanced data, closer points dominate, mitigating the, so if the point that is closer to me, so this is a like a green data and new data point has come, and if there are points like which are purple closer to me, and there are more red points here, even though, and we are taking like say 20, we are taking like 20. So even the purple are less and we have more red, but purple is more around green, so this will have more impact than the red data points. And if you are taking like k equal to 20 neighbors, so even though they are fewer in number, but they will have more impact. So that's what I'm giving you in this example. So mitigating the impact of imbalanced data. if your query points surrounded by 2 very close class A points and 3 distant class B points, then the weighted KNN will correctly pick class A. It will not just count that, okay, because class B has 3 and class A has 2, so I will pick B. No, it will not just count the number of the neighbors, it will also count their weight, how close you are to me. And that's the right way to do it. Okay, I hope this is clear. Okay, let's see an example, simple example, you will understand. So for example, there is a rabbit who has to decide what do I need to eat. So there is a close rabbit nearby which is at 0.1 meter or his friend. Okay, the distance is like friend. Okay, and he asks, like, he suggests that you should eat carrots. Okay, and there are 2 elephants, okay, which are farther away, 10 meter away, and they suggest that, okay, you should eat tree bark. So even though there are 2 and there are elephants and there is a rabbit which is only 1, their number is more, this rabbit will still choose to eat carrots because this friend is closer and that this friend has more impact or weight on the rabbit's decision. I hope this is clear. Okay, but the vanilla KNN, it will say no, eat tree bark only because they are more in number, because 2:1 elephant wins. So that's why this is an optimization or improvement over a naive KNN. Okay, let's see the next one. The next one is Mahalanobis distance. This is a very important concept. So Mahalanobis distance is an improvement over Euclidean distance where we also consider the covariance, because say for example makes assumption that all the features are independent. So we have multiple features, okay, which will decide my final output, right? The features are the input. So provide, and all of them provide unique information. They are independent of each other. That's the assumption for linear regression also, right? But that's not the case. For example, height and weight are highly correlated. As a person's height increases, the weight will also increase, right? But when we are taking Euclidean distance, then we'll consider height and weight separately. Okay, so in that way we are double counting the size of the person. The height and weight, they finally account for the size itself. So this is not a good representation, Euclidean. So for that, Mahalanobis distance is useful, and it will also measure the covariance between features. So if there is some correlation between features, so that will be captured by the covariance. So we have a covariance matrix. Okay, so this is like a covariance matrix, and then you will have, say you have features. So this will be like F11, variance of F11, F22, F33, like that till FDD. Okay, so all the diagonal elements will be the variance, and here it will be like F12, F13, like this till F1D, and here it will be like F21, F23, like that, and this will be like FD1, FD2. Okay, so this and this value F12 and F21 will be same. This is the covariance of feature 1 and 2. Okay, and all these are variances on the diagonal. These are the variances, that is variance of feature with itself, covariance of feature, that's the variance. So these are the diagonal elements will capture the variance, and all these will capture this F1D and D1 will be same. They are the variance of dth feature and first feature, so they will be same. So mostly always this covariance matrix is symmetric. Okay, so this will capture the variance between 2, and that is there in the real world. Okay. So this is also, so how do we calculate distance? So x minus y transpose into x minus y, this is in the matrix form. So generally x transpose x is equal to x square, okay, and square root of x transpose x, that's like the Euclidean distance. Okay, and then we are doing it in like vector matrix form, and here we are also introducing, this is the sigma inverse term. This is your covariance matrix that we put in the middle. Okay, if there is no correlation, then all these will be 0 0 0, all the non-diagonal elements will be 0, and that way it will be like, so if this is an identity matrix and all these covariances are 1, then Mahalanobis distance reduces to Euclidean distance itself. Okay, if identity matrix is what, all the diagonal elements are 1 1 1 1 and the star everything is 0. Okay, so this will become Euclidean distance itself. Okay, and if the diagonal matrix is if it's a diagonal matrix, then it will be normalized Euclidean distance, because we are taking an inverse, right? We are taking an inverse, so this will become reciprocals of these, and here all these this is identity is the giving the variance, means all the variances are 1 1 1. If they are non-zero, means the variances for each feature are non-zero. So for example, sigma 1 1 is say 5, sigma 2 2 is like 10, or whatever value. So all these diagonal elements are not 1, means there is some variance which is not equal to 1. That's what this is telling. Not important, get the concept, but that Mahalanobis distance also captures the covariance which is always present in the real world, say as height and weight are correlated. Okay, I'll give you a simple example, you will understand that. Say for example, we have this. So mostly the Euclidean distance, it considers everything is not correlated. That's why you see a circle, there is no variance. Okay, and this is your average person. Okay, and you see that this person who is like 7 feet tall and 120 kg. Okay, this is considered as an outlier because he's not in the circle. And this there must be a fat, small, short and fat, 5 feet and 110 kg, but still that will be in the normal range. Okay, but that is not a correct representation, because even this, for as the height increases the weight will increase, and this is a perfectly fine example, and this person is fine. Okay, he's not weird in some way, but this short person is weird with short height and a very big weight. So this is weird. So that's what Mahalanobis distance captures, that how weird you are. Okay, not following the trend. So again, the average person is fine, and here this is one Mahalanobis unit, means say for example 1 standard deviation away from this, so you're fine. So now if we are capturing, and this Mahalanobis distance will capture the covariance, so this will be like a ellipse. So now this athlete will come in the fine range, and this will be counted. Okay, you are fine now. And now this person B, which were like this 5 feet and 110 kg, that is like 5 Mahalanobis units away. So that is not in the picture itself, means you are an outlier, you are not normal, you are weird. That's what this Mahalanobis distance captures, how weird or not normal to the trend. You don't fit the normal. Even after capturing the covariance in the data. I hope this is clear now. Okay. And this is 5 units, you can say like it's like 5 sigma away, and you're an outlier. Okay, then if this is clear, let's move on. So runtime issues, let's see some runtime issues. So NAV KNN shifts all computation to inference time. As we said, everything is done at runtime, there is no training time here. All the distance calculation, everything is done at runtime, and the top k values are taken out from after sorting it. So to find the neighbor for one query, we must touch every single bit of the n cross d matrix, that is like n data points, and they are d-dimensional. So have to capture all the n data points and all the d dimensions for the distance, and then only we can calculate this how far you are from the data point, right, for all this. So that's why you have to go through all of this, and this will be like this, if it is n is equal to 10 to the power 9, that's like 1 billion. This will take seconds, but in real world we want milliseconds. Okay, so how to go around this? And for this will be solved by very advanced algorithms, okay, which I'll give you just a glimpse of, but I won't go in depth of it. Okay, let's see the advanced optimizations. So more advanced optimizations are, so there are distance weighted KNN is there. So there's KD trees, is one kind of tree data structure. Okay, when the d dimensions is less than 20, we can use this. Okay, it recursively partitions the space into axis aligned hyperrectangles. So if this is the space, right, it will partition the space into like this axis aligned hyperrectangles like this. And it will consider each space as different. Each hyperrectangle will be considered different, and we'll see whether the neighbor falls in this rectangle or not. Okay, and this distance will be measured like this. Okay, so this is your KD tree. Okay, and because of the tree data structure, all the searches will be now O log n search. So the search space will be divided into this hyperrectangles. So you can jump to the next rectangle instead of searching the complete area, that is like O n cross d. Okay, I don't know if it's visible there. So it is like here, and you have like axis like this. You have many rectangles, so the whole space is divided like this. And then you search in instead of searching in all. So because this is a tree data structure, you can go in, you can have some logic, and then search in one rectangle, the next rectangle, whichever follows your follows the logic. Okay, whichever fits our criteria. So because of this tree data structure, it will be following it will be giving us a log n search time, because it's being divided into, if it's a binary tree, then like that, trees are like this, right? So this will give us the log n search every time it's divided by 2 2 2. That's why DSA is important. So all these are DSA based. Ball trees, this is another kind of trees. So this is also used for very high dimensional data when d is greater than 20. D is greater than equal to 20. And here we use for example, we use Haversine distance for geospatial data. Haversine distance is nothing but the latitude longitude. Okay, so when we use latitude and longitude, okay, so that time that is used for geospatial data, and using that we calculate the, so it is using the sine and cos formula is there, sine phi cos phi formula. I don't remember the formula exactly, but you can look it up. So it will also account for the curve, because sine and cos is involved. It will also include the curvature of Earth's surface, and it will give you a correct measure. That's why this ball is there. Okay. Then there are series of approximate nearest neighbors. Okay. So there is local sensitive hashing. So it buckets hashes, okay, into buckets. Okay. So some a list of hashes depending upon whatever is the modular value. So it will bucket hashes together. And points that are close have high probability of having the same hash. And if they have the probability of having the same hash, then the probability of getting in the same bucket will also be very high. Okay, and then there's something called hierarchical navigable small world, HNSW. So here we create a graph of vectors. So we create a graph like structure. Okay, we create a graph like structure like this, something, it's not a tree. And then we go breadth first search, okay, across greedy walk. So we try finding the nearest neighbor or whatever is the logic here, and we try to find, we go through the level by level. We do breadth first search and we do a greedy walk to find the neighbors. Okay, so these are hierarchical navigable small world. Even FIRES uses this internally. So there, so Google scan. So this is product quantization. Here we reduce the memory footprint, because for the data is very high dimensional here. So the whole idea is to reduce the dimensions of the data. So we reduce the memory footprint of the high dimensional vectors. Okay, we use product quantization. So product quantization is like you reduce the, like for example, if you have a float 64, then this can be converted into, say for example, int 32. So you can quantize the units in which you are storing. So that is one kind of quantization. Okay, so it will reduce your memory footprint. So scan uses something called MIPS internally, and the FIRES also uses HNSW. So these are very important vector databases, very popular nowadays for all the RAG applications. So I'll create separate videos for them. I'll go in depth. But this is also kind of approximate neighbor search. Okay, approximate nearest neighbors, optimization over k nearest neighbors. And then we have dimensionality reduction to mitigate curse of dimensionality, which is your principal component analysis. So whenever you have high, so all these problems are like, whether you have to make the search faster, then you go for tree data structure, log in time it will give you KD trees and ball trees. And when you have very high dimensional data, then you try to bucketize it, use hashing, and then some kind of quantization, dimensionality reduction, so that the dimensions are reduced and they become manageable. Okay, so these are some broad takeaways from this whole advanced optimizations. Okay, so I'll create separate videos for scan and FIRES. In the future, PCA seen in the past, I'll create PCA video. We'll go through PCA again when we discuss in dimensionality reduction in unsupervised learning. We'll discuss PCA again there. But these two I'll create, and rest of the things are like data structures. Okay, thanks for watching this video. Have a great day ahead, and bye for now.